Thanks everybody for joining. My name is Timur. We have James with me on the line. And today we will be speaking about using high-throughput calculations and combining it with machine learning on the exabyte platform. This webinar is part of the ongoing series where we explain specific topics in using the platform. And the previous two sessions that we had in March and February were focusing on using the RESTful API and running high-throughput calculations. So now James will be reusing some of the content and will demonstrate how to apply machine learning based on high-throughput calculations that we attempted previously, and how to apply it for the purpose of studying adsorption. With that, James.
All righty, thank you for the introduction, Timur. All righty, so, oh, there we go. All righty, yep. So before we get into it, I just do want to reiterate that this is one of the advanced webinar series. We're going to be focusing on our API and how it can assist in computational chemistry. So because we're going to be heavily using the API, in order to use the API, a registration, being a registered user is required. Additionally, everyone that attends this webinar will receive a copy of it as a PDF, and we will also be uploading it to our YouTube channel after the fact. One more thing, I'm a huge fan of interactive webinars, so if at any point a question comes up, please feel free to use the Zoom tools to ask a question, and I'd be happy to answer. So I always like to start off by giving an agenda. So we're going to, so the first thing that we're going to do is we're going to give a background over adsorption, why we care about adsorption, why we're doing this. Then we're going to go into some high throughput optimizations of adsorption state geometries. And then finally, we'll do a little bit of machine learning using a recent data set from the literature of adsorption energies. So what is adsorption? Why should I care about adsorption? So adsorption is the process of molecules interacting with surfaces. For example, up here, we've got a water molecule on a silver 111 surface. But adsorption is one of those things that we interact with on a day-to-day basis. For example, water will adsorb to glass. So water will actually adsorb to glass, which I'm just kind of illustrating with this example over here. So water adsorbs to glass, and actually, if enough water adsorbs to the glass, it can end up forming it can actually end up condensing out into a new phase of water that's on the surface of the glass. So, and this is sort of caused by the adsorption of the water to the glass, leading to the formation of this new phase of water. And so it's one of those things that's encountered on the day-to-day of just typical general life. And so there's really two types of adsorption. Adsorption gets divided up into two categories. So there's chemadsorption, and the way to remember this is that chemical bonds are being formed typically during chemadsorption. Oftentimes it's very, very strong, but not always. And then physadsorption covers everything that isn't chemadsorption. So in physadsorption, the physical interactions other than chemical bonds are the ones that dominate, so electrostatics. And these are generally weak. They're not always weak, but typically they are. And those are the typical two categories of adsorption that we'll see when working with adsorption in the literature. Any sort of chemistry-focused talk discussing adsorption would be remiss without first going over the Sabatier principle, which is just one of those famous principles that connects adsorption energy to the reaction rate on a catalyst surface. There's sort of three different regimes on these volcano plots, as they're called, because they look like volcanoes. In the case where adsorption is way too weak to the surface, over here, which we're illustrating with this animation, let's say that for this binuclear reaction A and B on the surface, neither wants to adsorb. What we end up doing is we end up starving the surface of reactant, and that shuts down the reaction rate. If we go too far in the other extreme, though, like let's say we make B adsorb extremely strongly, but red still doesn't want to adsorb that strongly, or maybe B ends up blocking the side it doesn't want to desorb after the reaction or anything of that nature. What this can end up doing is poisoning the catalyst, which also shuts down the reaction rate because the reaction just isn't proceeding because blue is just binding way too strongly there. And then, but so really what we want is to be kind of in the center of the volcano here. We want to be just right in our adsorption energy according to the Sabatier principle, to get a good even mix of the two species on the surface to get a maximal reaction rate. And because it needs to be neither too weak nor too strong, but just right, oftentimes this is called the Goldilocks principle of surface catalysis, which just helps remember kind of what it actually says. So I hope I've motivated why we care about adsorption, especially in catalysis. Now I'll talk about how we can calculate these with DFT. So we don't need to do an experimental study to do this. We can do this on the computer. So for a system where we have A adsorbing onto B, for example, carbon dioxide adsorbing to this generic metal surface, we can just do 3 DFT calculations to be able to get this adsorption energy. So we first take the energy, we calculate the energy of the adsorbed state. So here, carbon dioxide on the surface, and then we subtract off the energy of the surface and the energy of the carbon dioxide, and whatever energy is left over, intuitively, would be the energy coming from the interaction between the two. Conceptually, another way we can think about this equation is that this is the energy required to separate the two to an infinite distance starting from the adsorbed state. So just 2 different ways of thinking about this, and how adsorption can be calculated computationally. And then finally, for our examples here, we're going to be mostly focusing on carbon monoxide onto copper, just because carbon monoxide is a very simple molecule, very easy to work with. And then copper is a very simple surface. It's just FCC. And so there's not a lot of complexity to be able to do these calculations. But also more importantly, carbon monoxide is pretty relevant to the carbon dioxide adsorption literature. Oftentimes it's seen as a side product of carbon dioxide it's oftentimes an intermediate in carbon dioxide reduction reactions, and also in many CO2 hydrogenation reactions to methanol. Oftentimes the reverse water gas shift will be a side reaction that occurs, which we're showing down here, where in the reverse water gas shift, carbon dioxide can get converted into carbon monoxide. Also on copper, it turns out that copper oxides, not metallic copper, but copper oxides, can actually catalyze the oxidation of carbon monoxide to carbon dioxide. So sort of going the other direction in the oxidation, so monoxide to dioxide this time. And so this proceeds via a Mars-Van Crevelen mechanism of catalysis. Mars-Van Crevelen is kind of the cousin to the Elie-Radiel mechanism of catalysis, except in this case, we actually deplete the catalyst of a species. So here we have carbon monoxide, and we have an actual oxygen that is part of the copper oxide surface. And we actually remove an oxygen from the copper oxide surface and desorb carbon dioxide, leaving behind actually a partially depleted copper oxide catalyst. And that's oftentimes noted using using a square box to show that we have depleted the catalyst, which means that there needs to be a replenishment step to restore that missing site in the catalyst. Copper oxide doesn't really oxidize carbon monoxide. However, at high temperatures, if oxygen is present, the copper surface will actually oxidize, which can allow this reaction to proceed. So it's still relevant to be looking at the adsorption of carbon monoxide to these things. All right, so that's helping to justify what we're going to be doing today. Before we jump into that, though, I do want to go over a little bit about the API and some key points, because we're going to be using the API quite a lot during this presentation. So to use the API, we need a set of keys. We need the equivalent of a username and password, and that's actually fairly easy to get. So starting from the home page, here we go. Starting from the home page, click the account icon in the upper left corner. Then we can go to account preferences. And if we scroll down a little bit, there's going to be a button called Generate API Token down here. And this will come up with a little pop-up window. And this will only ever be shown once. And this actually gives us an API token. It's only ever shown once, so make sure to go ahead and copy the account ID and the token. These are analogous to a username and password, and then paste them somewhere to remember them. So here we're pasting them into the settings.py file that's with our API examples repo. And so here we just paste them in, and then we save our notebook, because again, we only ever show these once. So in order to use our API, we have this concept of endpoints, which are just little helper classes inside of our API client that help do various operations with our platform. So here, from this window up here, we have our account ID, we have our account token. Again, these are analogous to a username and password. We have some information out here for the connection that typically doesn't really change that much. And then just to help keep things neat and tidy, we end up wrapping all of these arguments up into this endpoint args argument, which we unpack into the job endpoints when we create them here. And this is just for convenience. We could also just pass in a list as well. So this is how we can generate an endpoint in general. And so the parts of the API that we're actually going to be using, we're going to be using materials endpoints, which we can acquire very easily with this import statement here. Materials help work with materials that are on our platform. We're going to be uploading and downloading files from the platform. We're going to be managing sets of materials. So material sets are like folders of materials. We're going to be creating materials, copying them. We're going to be getting materials from the site. So all of this stuff. And then we're going to be using the workflow API quite a lot. So workflows are a set of repeatable operations to perform on something to get a calculation. These are essentially recipes for a calculation. For example, phonons and quantum espresso, that might be a workflow. Calculating the total energy using VASP might be another workflow, and these are applied to materials. Here's how we can import a workflow endpoint. And today we're going to be editing the JSON for workflows. We'll be creating workflows and we'll also be copying them. And then finally, jobs are the glue that bind together workflows and materials. And so the job endpoints, they let us submit jobs to the platform and get various information back about them. Here's how we can get them from API client endpoint jobs. We can import the job endpoint. And the parts of the job API that we're going to be using today, we're going to be creating jobs, we'll be submitting jobs, we'll be listing the files from jobs so we can download them, and we'll be getting compute parameters from the job. And so that's the parts of the API that we'll be using today. And then one last note before we jump into things. Most of the API functions that we'll be using today and what we'll be showing can actually take an organization ID as an argument. And so what this does is this really helps facilitate collaboration because I can run a calculation or I can upload materials to my organization, and then other members of my organization can have access to that. And so in order to get this organization ID, what I can do is I can first log onto the platform, change my account to one of my organizations. For example, I'm a member of the exabyte organization, so I go there. I then find a job that my organization has run and I copy the job ID, which we can find in the URL. And then I just paste it into this little snippet of code and it'll print out the organization ID to my console. And so that's how we can get an organization ID. All right, so now that the API is out of the way, now we can start getting into optimizing some of these adsorbed states. Just one second. Sorry about that. All right, so to start off, in the last webinar, as Tamer mentioned, we did this high throughput screening of copper slabs. And so we can actually reuse this work that we did in the last webinar, and we can run our adsorption calculations on these because these are already optimized. We've already calculated the energies of these. We've already done half the work already for these. And so to be able to do that, the first thing that we do is we're going to be downloading the slabs. Also, as a side note, all of this code is going to be available on our GitHub repository as part of the API examples webinar. So don't worry too much about writing down line by line everything what's going on. This will be accessible after the webinar completes. So the first thing that we do to download the slabs is we import a bunch of stuff to make this notebook work. We also will pip install any packages that are required to make this example work. And then the first thing we do is we run this little box of code here. It looks intimidating, but really what's going on is we just create our job endpoint, we create a material endpoint, we declare this job data class out here. This is just a data class that contains a lot of information to help us keep track of an individual job. So things like the job's name, the termination, the Miller index of the surface, the symbol, etc. Here I declare a list of job IDs from the slabs in the last webinar. And then here I just use a list comprehension to loop through all of these IDs and generate job objects. And so then we can run that cell. And then the cell will complete. And then we can actually download the slab from our platform using this code right here. So here in this code, we declare the job's file name. We use this download contcar function, which will appear in our API examples. And all this function does is give it a jobs ID, a job endpoint, and the file name. This will actually download the contcar from the VASP job. For those that are not as used to VASP, by the way, contcar is the final relaxed geometry that VASP gives out. So it's the sort of the final relaxed state. And so that's why we're getting the contcar, because it's the relaxed slab. And then we do that, and we can read in the structure into memory as an ASE atoms object. And so now that we have a collection of slabs, we can start thinking about how do we want to set up these adsorption calculations. So one important consideration to make is the idea of lateral interactions in these slabs. So it turns out that if I've got because we have repeating images of these slabs, particularly in the A and B direction in our slab, repeating images of our adsorbates can actually interact with one another. In some cases, that might be desirable, such as a surface coverage study to see how carbon monoxide interacts when a lot of it's adsorbing. But in our case, we just want the energy of a single carbon monoxide onto the surface, and that can be the fix is fairly easy. It can be accomplished by just making sure that the periodic box in the A and B directions is large enough to mitigate these interactions. One important thing to consider is also when we resize these boxes, it's really important to remember the stoichiometry whenever we go back and do that adsorption calculation. It's a bit of a spoiler. We'll be coming back to this point in the future. So now that we've kind of come up with our strategy for how we want to do this, the first thing that we can do is we can start expanding these. We can expand these lattices out, as I mentioned on the previous slide. No, that's a typo. Actually, what we're doing up here, I'll have to fix that typo when we upload the notebook. We're not generating a PyMatGen object here. We're actually doing that expansion in the A and B direction to make our computational box large enough. Here, what we do is we say, if the A or B direction is less than 5 angstroms, we'll just add an extra repeating unit in that direction. So if it's small, we add another repeating unit in one direction, and then we just run this check in both A and B. And so this will give us some slightly larger slabs for some of these to help mitigate the lateral interactions. After we resize our slabs, we can then go through and automatically detect surface sites here. In this case, we actually take a very simple strategy where we consider a surface site in this function right here. We pass in an ASC structure and a list of coordination numbers for every atom in the slab. And what we do here is we consider that if the atom in the slab is undercoordinated in this case, recall that we're using copper. In the bulk, copper will have 12 bonds. So if it has fewer than 12 bonds, it must be on the surface if we actually properly relax those slabs in the last webinar. And here is just in addition to this, we just have an extra checkup here just to say, hey, I only want one side of the slab. So we only are putting carbon monoxide on one side of the slab. And so then we do that and we say, hey, if it passes this checkup here, so undercoordinated on one side of the slab, we will actually save the index of the surface just to tag it as this is an actual site. And then here we just go ahead and loop through the jobs. We use ASC's built-in neighbor list function to calculate our coordination numbers by binning them with NumPy. And then we apply this function to the list of coordination numbers to generate a list of surface sites. So it's worth noting here, by the way, that we don't have a strategy in place to detect non-unique sites. That would be the next step here. But just for simplicity and to keep things within a 45-minute webinar, we don't take that approach. But that would certainly be the next step to take here. And then once we have our list of surface sites, then we can actually go into placing the carbon monoxide, which we do here. And so here, the way that we place the carbon monoxide is actually fairly simple. Oh, I didn't want to do that. Let's actually go back to where we were. Here we go. The way that we place the carbon monoxide is fairly simple. We have this function called place carbon monoxide molecule. In this function here, we just take a job and we take in that index of the site that we calculated in the last one. So we take in the site that we tagged in the last slide. And we say, okay, let's get the coordination, or let's get the coordinates of the site that we identified, which we do here using AFC. We place the carbon atom. So by taking the site's coordinates and then going 1.43 angstroms up in the C direction, and we place a carbon atom there. And then we go 1.43 angstroms more up and we place the oxygen atom. We chose 1.43 angstroms here, by the way, as just an initial guess of where the atoms might be. In the gas phase, 1.43 angstroms is the bond length of between carbon and oxygen and carbon monoxide. And so then we save this carbon monoxide atom and we append it to the slab that we had on a site. And so then this is sort of how we're placing the carbon monoxide. And then finally, just to help speed up convergence, this is a common trick that's seen in the literature. We'll just fix every atom and every copper atom in the slab so that only the carbon monoxide actually moves, just to help speed up convergence of our geometry. And so then when we do that, we get quite a lot of surface sites. Just a little movie here showing the different sites. So again, we didn't check for non-unique sites, and actually coming up, we have the 111 surface here. All four sites in that 111 surface are actually the same site, and so that's certainly one important consideration to make in production level work is how to filter out unique sites. Oftentimes, it's done by hand, or in some systems, an algorithm can be generated to detect that. So now that we have our list of slabs, we can go ahead and start thinking about submitting these to the platform. And so in order to submit a job to the platform, I need a workflow, I need a material, and I need a job. And so that's what we're going to be generating here. So here, the first thing that we do is we go ahead and we create our workflow after we create our workflow. In order to do that, we remember that in the last webinar, we already set up these calculations to relax slabs, and the only change we're making to that calculation is we now want to freeze some of these atoms. And so we can accomplish that by doing this. So here we just have the bank workflow ID of what we did in the last webinar, that workflow. We set up our bank workflow endpoint and we copy it into our organization account. And then we just make one minor change to the postcar file of that workflow. So here we just loop through the different units in the workflow, and we say, hey, if it's the postcar, we're going to take in the postcar with constraints. So this is just a Jinja templated variable here that the application provides. And so this just tells the web app that, hey, we need to include selective dynamics when we write the postcar. Selective dynamics being the option in postcars that tells VASP that I want to freeze certain atoms. So then we can create our workflow endpoint. We can give our workflow a friendly name, so constrained adsorbate relaxation, and we can go ahead and create our workflow on our account. Oh, didn't want to do that. Come on. Here we go. And then, yeah, now we're back to where we were. Okay. Oh, keynote. Alrighty, so next up, we can go ahead and upload materials. So we need to get the materials onto the platform if we want to do any science with them. And so the first thing we can do is, just to keep things neat and tidy, we can create a material set, which is essentially a folder to keep all of these slabs that we're going to upload organized. We're going to call it Webinar Copper Slabs, and we're going to put it onto our organizational account. So then we can just go ahead and loop through all of these slabs that we've made. We can upload them to the platform, and we can copy them into that material endpoint and keep track of their ID on the platform. And then next up, we can actually go through and create the jobs and submit them. And that's what this does out here. We start off by getting a project ID to assign these jobs to using this code snippet. And then we loop through all of our jobs, all of the sites in our jobs, and we say, okay, let's set up our computational information up here. What this code up here is doing is, this is just saying that if it's a system with a lot of atoms, we'll give it an extra computational node. So some of these will be getting 32 cores total, so 2 nodes of 16 cores each. Here is our computational information right here. We set up the computational information. We give it we set up these compute parameters using our endpoint. we specify our workflow, we specify our material, and then we can just use our job endpoint, passing in all of this information that we've gotten, and we can go ahead and specify the adsorption job. And we can just keep track of the job ID. And then down here, all that we do is we just loop through all of the job IDs that we've got, and we go ahead and submit the jobs. And so that's how we can set up all these jobs. These jobs will start on the platform. So over here is an example of one of these. And here's the actual optimized adsorption state that this yields. So a copper slab with a carbon monoxide on the surface of it. And so then now we've got all the things that we need to actually do an adsorption calculation using that equation. And that's what this function up here does. Is given the adsorption, the ID of an adsorbate, the ID of the adsorbent, so the slab in our case, and the ID of the complex, we can go through, we can pull the energy out from the from the VASP calculation. We can use that adsorption energy equation that we showed before and return an adsorption energy. And if we do that for carbon monoxide, our complex here, and our surface, we get minus 60 EVs as our adsorption energy. Which after a quick thought, that might not make too much sense. In the real world, if we blow carbon monoxide over a copper surface, the copper surface doesn't get red hot. So clearly something is going on here. And indeed, that is what's going on. And this is just illustrating a pretty common failure mode in these calculations, where a common mistake is to compare systems without remembering the stoichiometry. Or in other words, there's differences in the electron counts between systems is what's going on here. So remember that we actually had to we resized some of these slabs, including this slab, to try to mitigate those lateral interactions. In doing so, we increased the number of copper atoms in our complex. So now there's a different number of copper atoms in our complex versus in the slab, which we can kind of show here. Here's the energy of carbon monoxide. Here's the energy of the complex. Here's the energy of the slab. We can see that the complex up here is like twice as large as the energy of the slab. So something's clearly wrong. And indeed, if we actually rerun a single point calculation, but after removing carbon monoxide and just recalculating the energy of these resized slabs, we get a much more reasonable energy out here, because now we're comparing stoichiometrically equivalent systems here. And we get about half of an EV is the adsorption energy of carbon monoxide to the copper slab, and that's much more reasonable for this system. And so that's how we can do these sorts of high throughput adsorption studies to generate a lot of data, and then just going over a very important consideration to make. If things are going wrong, check the stoichiometry, is sort of the moral of this slide. So now what we can do is we can actually go into a little bit of machine learning now, because machine learning adsorption energy has actually been a hot topic in the last several years in the literature. So I'm just going to go over that with a few recent models of adsorption that have appeared in the literature over the last decade. So in 2010, the surface curvature model came out. What this does is this is for nanoparticles, and it connects the adsorption energy of adsorbates to the actual geometry of the binding site on nanoparticles. Specifically, the curvature of the surface and the coordination number of the binding site. Related to this is the generalized coordination number. The generalized coordination number is another geometry-based metric that sort of takes into account how under-coordinated is the site relative to what it should be in the bulk. So very, very useful indeed. Additionally, in 2018, there was the rolling model of adsorption, where they actually take into account the relative stability the relative stability of a particular site in a nanoparticle. Conceptually, what they're doing is they're taking the energy required to separate out an atom in the nanoparticle, and that's a descriptor of adsorption that they're using to get really nice relations between the they call it the delta E of the metal and the energy of adsorption. And then finally, out here is a model from Dean et al. In Science Advances, where they actually considered a few different descriptors that they came up with to generate to predict the adsorption of several species to several D9 transition metal nanoparticles. So here's an illustration from their SI. that's just describing what's going on there. So we take a selection of 162 examples from the data set that they published. Of methyl, hydroxyl, and carbon monoxide adsorbing to copper, silver, or gold nanoparticles in a variety of different morphologies and sizes, which we're illustrating up here. Here's sort of what the data set looks like. We get a binding energy, we get the local cohesive energy, the chemical potential under HSAB theory, and the metal adsorbate binding energy in the gas phase. What does any of that mean? Well, that's what this slide will kind of go over. So the CE local descriptor, essentially what this is derived from is the bond-centric model of nanoparticle stability that they took and actually applied to this problem. So under the bond-centric model, there's actually an approximation for the bond energy of any bond in a metal nanoparticle. And so here, what this descriptor is for a metal atom in the nanoparticle, imagine cutting every bond that's connecting that metal atom to the nanoparticle, and then adding up all of those bond energies that we broke by approximating them with the bond-centric model. And so in principle, what this is doing is this is giving us a descriptor of the relative stability of the binding site. Over here is the chemical potential of the adsorbate. In the paper, they call this IPEA because it is the ionization potential and the electron affinity, so IPEA is where that comes from. And it's the negative average of the two. Under HSAB theory, this is actually a central differencing approximation of the chemical potential. And then finally, they have this gas phase binding energy of the adsorbate to the metal and to a single metal atom in the gas phase. They call this MADS because it's the metal adsorbate binding energy, but in principle, it's just a gas phase binding energy. And what these descriptors give us is that these two descriptors, the chemical potential and the binding energy in the gas phase, these give us a descriptor for the relative stability of the adsorbate. And then the gas phase binding energy and the local cohesive energy, these give us a descriptor of the relative stability of the metal and the binding site. So definitely useful indeed. And so then what we'll do is we'll actually generate a couple models and then we'll compare them to the regression that the Science Advances paper got. And so this is another notebook that'll actually appear on our API examples repo here, this model selection and tuning workflow here, or notebook here. So the first thing that we do is we import some stuff from sklearn, a few models. We import matplotlib and other things. Then we go down and we can actually load the data into memory. So we have a CSV containing the data from the Science Advances paper. We just declare the target column name and we read the data into memory. And then after we do that, we do a train test split. So an 80-20 train test split. So about 30 or so of these examples are going to be held out as a testing set. Then we can standardize the data. So in standardization, we scale each column so that it has a mean of 0 and a standard deviation of 1. It's a fairly easy operation to do, but it's very good at helping make a lot of these machine learning models work better. It's just something easy to do that just makes things better in general. And so highly recommend doing that for any machine learning problem, unless there's a good reason not to. And then what we do out here is we just compare 3 different models. So we look at ridge regression, we look at a kernelized ridge regression, and we look at a really simple neural network model. And so we declare the models out here. We loop through all of them, we fit the models to our data, and then we pull out the root mean squared error as our error metric. And then we just say, hey, the model that has the best RMSE is the model that performs the best on the data set. In our case, it's actually kernelized ridge regression that performs the best. And so then out here, we actually can draw a parity plot of the data. And let me just go back to that. Here we go. Yeah, here's a parity plot of the data of predicted versus actual values. And so to generate that parity plot actually, and to do all of this, by the way, we don't actually have to know any programming. A recent feature that we actually added to the website is a new built-in machine learning capability. So here's actually how we can do this on the platform. We have video tutorials for this, by the way, so don't worry too much about following along exactly. On our documentation, we have tutorials showing in detail exactly how to set these up. But in principle, what we're doing here is we are copying a machine learning workflow. We're going to rename it to Python ML KRR for kernelized ridge regression. And then we're going to create a kernelized ridge regression workflow that we can then reuse forever on any different data set that we want. So here we just select kernel ridge as the model. Just scrolling down here to show that it really is kernel ridge using scikit-learn. And then we can go up here and we can actually save our workflow to our account. And then now we have something that'll actually train kernel ridge regression models and add them to our account as many times as we want. So we can then select this when creating a job. We'll get this new dataset tab. We'll rename it to like webinar training. We can go and select a dataset, which I've already uploaded to the platform like any good TV chef. And so then we can go down here. We can give it the target column name in configuring the workflow. We can say, yeah, this looks good. Let's save this job up here. And so then this will appear in a pending status on our jobs page. We can submit the job, and this will actually train the kernel ridge regression model on that Science Advances data set and save it to our account. And not only that, but it'll also give us the parity plot that we saw on the last slide. So without needing to know any programming, I was able to train a kernelized ridge regression model and get a parity plot out of it. And finally, comparing to the literature dataset, we find that kernel ridge regression performs pretty similarly to the literature dataset. So over here, blue is our training set, green is our testing set. Over here, they're actually coloring by the different adsorbate and the different shapes or the different nanoparticle shapes. Their error bars also were generated using cross-validation. And so we see pretty good agreement, which makes sense because OLS and ridge regression are very related to one another. Ridge regression is just linear regression where there's an extra penalty term for having too much weight on one coefficient. And kernelizing it is just adding a kernel to the data. And so very similar models, so it makes sense that we would get similar performance. So just to summarize what we have learned in this webinar here, we've learned how to calculate adsorption energies. We've learned how to optimize adsorption configurations, how to use machine learning to predict physical properties given a data set. We've also leveraged the web interface to set up a machine learning workflow and perform machine learning without needing to do any coding on our own. And so very, very useful things to be able to do indeed. The next webinar will be the third Friday of next month. Keep posted for that. The code for this webinar will actually be available on our GitHub. Additionally, we're going to be doing a Q&A in just a second, but if a question comes up after the webinar, right after we end, feel free to reach out to info@exabyte.io, and we'd be happy to answer any questions. Thank you, and if there are any questions, I'd be happy to answer them. Thank you.
Thank you, James. Let's see if you have any questions in the chat. Nothing in the Q&A yet. The last part about how we can use the platform to do machine learning calculations was a bit too fast. Maybe let's come back to it and go through it a little. The next one.
Here, this one, yeah.
All right. So let's go back to the data set upload.
Ah, yes.
Starting from there.
Okay, yeah. So here, this is actually a new feature that that we introduced as part of this update. So instead of a materials tab, if we have a machine learning workflow, we now have this dataset tab that actually shows a preview of the data. And also in addition to that, we actually can select a data set as part of a workflow. So we've actually replaced the select material button here with a select data set button, just because that's more relevant to what we're doing here than selecting a material. So
for a specific workflow, for machine learning workflows.
Yeah, and so any machine learning workflow that we declare will actually have this this feature out here. So because I copied the machine learning workflow and just edited it, it copies over that property that tells the platform, hey, this is a machine learning workflow. And so then when we go to actually select these data sets up here, On this pop-up that we get, we can upload files, we can delete files, we can select them out here, and these are just files that are on my account's Dropbox. There's definitely a lot out here because I was doing a lot of testing as we were developing this with different machine learning techniques. Over here, data to train with, this is just that Science Advances data set that I uploaded. And so it's fairly easy to select a data set for machine learning. I just click on it and it comes up. And we get this really nice preview up here of a table showing the data that we're about to train on in the column names. So here is the binding energy according to PBE. Here's that CE local column, chemical potential, the MADS. And so because I want to train on this PBE binding energy here, what I need to do is I have to tell the workflow, hey, I want to do this. So all that I do is I go to the machine learning sub-workflow, and under important settings, I specify the target column name to PBE BEEV. Same column name is on the dataset tab, and this tells the workflow, hey, this is what we're training.
Maybe let's come back to the top of this, just rewind a little bit. Yep, and let's explain the general structure of this workflow.
Okay, yeah, certainly. So there's two sub-workflows here. There's the setup the job sub-workflow, which might be down here. Here we go. Okay, so there's the setup the job sub-workflow up here. So the setup the job sub-workflow, all that this does is this handles all of the backend stuff that's needed to make this work. It doesn't need to be edited by the user, but what it does is it carries information over whether we're training or predicting a workflow. It also copies over the data set into the jobs working directory. And so then over here in this machine learning workflow, let's see if we get like a larger view of this thing. We don't. But in principle, what these individual units are here in the machine learning sub-workflow is this setup pack variables and packages. This is just a general settings configuration that we use for the rest of the Python stuff. Data input will read in the CSV. We'll actually read in the CSV that we've copied into the working directory. Train test split out here. We'll actually split our data into a training and testing set. So data standardize out here will actually standardize our data as we did in the notebook. This is actually all mirroring what we were doing in the notebook, where we read in the data, we had the training and testing split, we had the data standardization. Here in this, I don't actually scroll down into this video to show it, but this is actually the model workflow unit where we train the model. And then here is actually the unit that creates the parity plot that I showed on the next slide.
So we have a set of logical blocks that are reusable. And this workflow now represents certain arrangements of these logical blocks that actually execute the logic inside the machine learning, the training process of a machine learning model. Yep.
Yeah, and I like the idea of logical blocks. I always like to think about these like Legos, where we can actually remove one and add another one. So here I actually show an example of that when setting up this workflow unit here, where I replace a neural network regressor with a kernelized ridge regression regressor. But really, any of these models I could have also chosen. I could have been regressing using a random forest or ADA boosted trees or anything of that nature. These are very much like Lego blocks where I can just remove one, add one in to suit whatever machine learning problem I have posed.
Okay. And then at the end, when we get to the result of this, we have the train test split in the plot.
Yeah, here's
well,
actually.
let's go back a little bit to see the workflow as well, right? So the train model will appear as a workflow under their account.
Yeah, this actually lets them reuse the workflow for new data. So now, if I wanted to make a prediction for a new system that I had never seen before, all that I would have to do is give it the columns that I trained the model on, and then I would give it the workflow, or I would give it the columns to train the model on, and then I would say create a job using this ML predict workflow here. And then I would create new predictions using this trained kernel ridge regression model that we trained as part of this job here.
Okay. Yeah, I think that clarifies some of the questions that people may have. There is another question in the Q&A.
Oh yeah, I see that. Okay. All right. So the question is, alrighty. So are there any memory limitations associated with the size of the data set that can be handled on the platform? For instance, if I have a folder of images, the size can increase quite quickly. Currently, the only limitation would be the amount of storage that an account has available. I believe by default, it's like 20 gigs. And then the upload size of an individual file is currently 20 megabytes. In terms of memory limitations, though, that would be based on the actual compute resources being used. So different node configurations will have different amounts of memory available. For example, the debug queues have less memory than an OR8 queue, for example. I hope that answers the question.
Yeah, I think there is quite a bit of information on our documentation online about the computational resources that we have. And if the memory is a concern, then we could use the queues that have the larger memory resources with more cores, and that should help resolve the issue. We also have GPU-enabled resources to help speed up some of the machine learning workflows. Okay. All right. Maybe since there are no more questions, let's try and help users navigate to sources of documentation. We have two main sources, right? The API examples repository and our actual documentation online.
Yes.
Maybe spend a minute to explain how to find those.
Okay. Should I just open up a browser and just go to them, or?
Yep. Let's
do that. Sure. Let's go ahead and stop the presentation. We can go over here. All right. So in order to get to our documentation, the link is docs.exabyte.io, which we're showing up here. And so we can go here, and this will give us a documentation page. And so if, for example, we want a tutorial on how to do machine learning, we can go here to tutorials, Python ML. And this train model tutorial will actually repeat the example that we had in the webinar today, where we go ahead and train a neural network on this data from Science Advances. We generate a parity plot, etc. In order to find the memory limitations of different nodes, what we can do is go to AWS out here to queues. Yeah, so there's this queues page out here. Here we go. Yeah, so I can go to like Amazon Web Services and I can see the hardware specifications for each queue here. So under AWS, we have quite a lot of queues available. Here's the memory limitations in gigabytes. The GPU queues have a lot more memory available here. So here, for example, there's like almost half a terabyte of memory available for this GPU queue out here. So definitely a lot of memory that can be gained out there. That is the documentation there. So generally very helpful. And we also have on our GitHub page an API examples page. So here it's just github.com/exabyte-io exabyte API examples. And if we go here, we actually get a nice curated list of examples from these webinars. I don't think we've merged in this. We haven't merged in this talk just yet, but in general, we can go to the examples here. We can go to like any of these. So here's like the webinar from last week, for example, where we created some Gamma Illumina slabs, and we can open up the notebook either on our machine or using GitHub. GitHub will actually render these notebooks.
Sometimes it does.
Well, it's not our fault. That is GitHub's fault.
Right. That's a known feature. Okay. Looks like we have no more questions. If there's nothing else to cover, then we'll say thanks to everybody, and we'll see each other next month.
Thank you all for attending.
Thank you, everybody. We'll make the videos and the PDF of this current webinar available to you shortly. With that, take care, everybody.